Hi, in this video we're going to be finishing our discussion of chapter 14 of Stewart, which is all about Lagrange multipliers. Now, this is another technique for maximizing a function on a boundary. The other way of thinking about that situation is that idea. We want to find the max or the min, or and the min, of a function subject to a constraint. And again, that constraint could be a boundary of a region, like we were doing at the end of chapter 14.7, or it could just be the constraint, like you have only a limited amount of surface area of a box and you want to maximize the volume, or a perimeter and you want to maximize the area. That old problem that you've done probably every year of math your whole life. So the way we're going to set this up now in a much more interesting, so to speak, situation, we have a function f of xy equals z. This is giving us a surface. This is a surface in 3D space. It has 2D input, a third output, and a height. And we have a constraining equation, some other function g that's already equal to a fixed value. Let's call it k. So this is your constraint. Sorry, and this is what we're thinking of as the function in that idea sentence up there. Now, what does this constraint represent in a 3D landscape? You've seen that kind of equation before. A surface equation with the output fixed is what we would call a level curve to some other surface, g of xy equals z, right? Some other surface. We're trying to see or understand, under this constraint, what is the biggest value or the smallest value I could get out of my function. So we're trying to figure out, under this constraint for this level curve, what is the biggest value for this, the output? And that might give you the idea to start thinking about, consider f of xy equals different output conditions. And what would these all be? These would be level curves of f. And this might all look rather arbitrary, but we're just going to keep guessing, basically. And these would create level curves. And now we're in a situation where we have a level curve for g over here and level curves for f over here. So for one's going to use red axes, because once we're all in this level curve space, well, maybe we can just think about what it looks like in the xy axis. So these level curves for f are the regions, are the boundary lines of space where f has specific z values, specific outputs. Whereas the constraint function g equals k is some other guy, other blob like this. That's the g function. That's g of xy equals k. And you would notice the point where we are on both of them and we have the biggest outputs for f would be the point where they are basically tangent in a way, right? When they're basically tangent to each other. Now, when they are tangent, what would also be true is that they would also have parallel normal lines. And that's the key observation, because we understand that tangent lines here are hard, but normal lines, we have a powerful tool in our toolbox that gives us normal lines very easily. Specifically, so if f is maximized under G, under the G constraint, their normal lines are parallel. Now, why do we care about normal lines, not tangent lines? Because, again, normal lines are the easy ones to get. Now, how do we get the normal lines of these surfaces? How do we get the normal lines to level curves of surfaces? Well, it would be that the gradient of f had to be parallel to the gradient of G at that same specific xy coordinate. What does it mean for these two? If these are vectors to be parallel, it would mean that, I'm going to write it out differently. For some scalar lambda, the gradient of f would be equal to lambda times the gradient of G. And that's the idea of a Lagrange multiplier. This is the multiplier in the title of the lesson. And this was Lagrange's insight, probably shared by other people, but he's the one who gets the credit in our discourse for some reason. And that's the pure idea. You're going to set these two gradients equal to each other under some multiplier, and we're going to solve for either the multiplier or the x and y's themselves. Without further ado, so here's the surface I want to maximize. Just xy. The wild function we talked about before. That's hard to talk about in having a saddle or a relative max or relative min. Under 2x plus 3y equals 6. Okay, now that's just a line in 2D space. But it's easier to think about, like most things, like we talked about in 14.6, as the level curve of a particular function g. So we're going to let g equal 2x plus 3y. Now, what is the gradient of f? And remember, this is a vector. The gradient of f would be the partial derivative with respect to x, y in the I direction, plus the partial derivative with respect to y in the j direction. The gradient of g, on the other hand, is going to be very easy, just 2i plus 3j. So the scalar multiple equation, the whole idea of this lesson is that we want to help set these two equal to each other so that the gradients, the normals, are parallel, and so that they'll be just touching. Well, that's relatively easy now. It's y I hat plus x j hat equals lambda times 2i hat plus 3j hat. So whenever you have a vector equation, this is two scalar equations. this gives us two scalar equations. This is y equals 2 lambda and x equals 3 lambda. Bunch of different ways to do this. A lot of the times it's going to be easiest to solve for x and y and then plug it into our constraint equation, which is 2x plus 3y equals 6. Now, x and y are already solved for, so we get 2 times 3 lambda plus 3 times 2 lambda equals 6. Or 6 lambda plus 6 lambda equals 6, which says that lambda equals 1/2. If lambda equals 1/2, careful with your lambdas and your x's, then x equals 3/2, y equals 1. And so we found the critical point of 3/2, 1 in a new, unique way. That's the only critical point on this constraint for this surface. And the f value at that point is very easy to compute. It's just 3/2. And so what that represents, that's the point where this constraint is satisfied that is on this function. Now, again, there's lots of other ways you could have solved this thing because it's a relatively simple set of circumstances. The real power of this comes into play when we're dealing with 3D functions. But again, the steps, just to go over it, usually we will define g, set their gradients equal to each other, subject to multiplying by lambda, solve for x and y, and then plug into the constraint equation, even if we have 3 variables. I'm going to do the next one without I, j, and k, just to show you it can look one way or the other. It doesn't really matter. Sometimes it's easier if you set it up as vectors with bracket notation, component notation. But here we go. So if you felt comfortable with what we did in the last example, feel free to go at it here. But here's the real use of Lagrange multipliers. It's when you're dealing with multiple variables. So this is a 4D function. You could say a 4D surface, but who knows what that means. Under the constraint x squared plus 2y squared plus 4z squared equals 1. Okay? So immediately take your constraint equation and turn it into a level curve of some other 4D function so you don't have to have that headache. We want to find the gradients. The gradient of f in component notation is going to be 1, 2, -2. The gradient of g is going to be 2x, 4y, 8z. So when I set the gradient of f equal to lambda times the gradient of g, I'm going to get 1 equals 2x lambda, the x components, and again, remember to multiply by lambda. 2 equals 4y lambda, and -2 equals 8z lambda. Maybe this looks mystifying. I encourage you to always write down the constraint equation one more time, just so you can see it. Usually that's going to be our key. We're going to solve, try to get x, y, and z eliminated or ready to be substituted out by solving each of these equations for x, y, and z. It looks pretty easy to do. X equals 1 over 2 lambda. Y equals 1 over 4 lambda. Z equals, this is also 1 over 2 lambda. And z equals negative 1 over 4 lambda. Careful. So it won't always work out that easy. I'm going to make sure to do one more example like that. But in general, this is the best technique. There's lots of other techniques you can use with cases and stuff. I'll show that in some of the answer keys I release. But in general, this is the easiest way I've seen most students approach Lagrange multipliers. With those solved for, you would get 1 over 2 lambda squared plus 2 times 1 over 2 lambda squared plus 4 times negative 1 over 4 lambda quantity squared equals 1. Don't forget the equals 1. So 1 over 4 lambda squared, 1 over 2 lambda squared, and this is also 1 over 4 lambda squared. Recommend clearing denominators just to make life simple. So we're going to multiply this whole equation times 4 lambda squared, getting 1 plus 2 plus 1 equals 4 lambda squared. This is 4, so 1 equals lambda squared, and lambda is either 1 or negative 1. So much more intense than the last problem. There's now 2 options for lambda. There's 2 options for lambda. Does that make anything super more complicated? Not really. I'm just trying to get a nice lambda. In the world where lambda equals 1, we're dealing with x equals 1/2, y equals 1/2, and z equals negative 1/4. So a critical point of 1/2, 1/2, negative 1/4. And the function value at that point would be 2. In the world where lambda equals negative 1, we'd have the critical point of negative 1/2, negative 1/2, positive 1/4. And f at that point is negative 2. What does this mean? These are the 2 values that work for our constraint, but more specifically, this is a min and this is a max. Okay, so if you're looking for the maximum temperature, it would occur at this point in space. If you're looking for the minimum temperature, that point in space. Now, if you're saying, well, I don't understand, how would there be a max point, max temperature in space? What do we mean? Well, we would mean if this is supposed to be our temperature model, this could be our constraint of like, well, this is the path we're going to take, right? This is the path we're going to travel in space, or our exploration region, I suppose, right? Because this would be a surface in space, a level surface. One more example where the algebra will get a little more interesting. And I encourage you to try this as much as you can on your own, because the homework can be a frustrating experience for students. It's better to have the frustration now when you're going to get the answers immediately. I mean, I guess you can always just steal a look at my key, but where's the fun in that? X squared plus xy plus y squared, subject to the constraint x squared plus y squared equals 8. Now you might be saying, how could this be complicated? there's only two variables now. Well, again, here we go. It's complicated because this equation, if f gets complicated or g gets complicated in terms of what its gradient will look like, that's where you'll start to see issues arise. Dun, dun, dun. So we're going to let g of xy always declare what g of xy is going to be. It should be really obvious. It's the stuff that's not a constant, but make sure you declare it. The gradient of f, I'll just go back to the ijk notation because I think it's more complicated, but it's very apparent that it is more complicated, that we're dealing with something more interesting going on. This will be 2x plus y in the I direction plus x plus 2y in the j direction. Whereas the gradient for g is a much more simple function, 2x in the I and 2y in the j. So when we're trying to set their gradients parallel, so their normal vectors are parallel, what are we going to get? We're going to get 2x plus y equals 2x lambda. That right there is pretty clear as to the source of our issues. It's going to be very hard to solve for x or solve for y when we have an equation that looks like that. But you can persevere through this, I promise. The j components give us the equation x plus 2y equals 2y lambda. And again, we know x squared plus y squared equals 8. Those are the three equations we have to work with. So, I recommend, as always, looking for factoring opportunities. I see a 2x here and a 2x here. So I'm going to take this top equation and actually try to solve for y. 2x lambda minus 2x. Now, why am I doing that? Because, again, we can factor out the 2x. And so we get 2x lambda minus 1. You can notice that down here, the same thing's happening with the y's. So I can solve for x and get 2y lambda minus 2y times lambda minus 1. When you're in this situation, now I'm going to take this x value and replace it with this x value over here. So I'm going to get y equals 2 times 2y times lambda minus 1 times lambda minus 1. You could have done the same thing with x's, but careful. Right now I'm worried that some of you might have gone ahead and tried to divide by y. That's a really bad move. Factoring. Let's clean up this right-hand side. That's 4y times lambda minus 1 quantity squared. 4y lambda minus 1 squared minus y. 0 equals y times 4 lambda minus 1 squared minus 1. Why do we factor? Because, as always, this shows there are two ways out of here. Either y equals 0 or this other thing, which is not lambda equals 0. If y equals 0, for a number of reasons we'd have an issue. So one easy thing to do is you would see x would have to be plus or minus root 8. But you'd also see that x would have to be 0. This is fundamentally inconsistent. Y equals 0 is not really possible. we have conflict here. We have one equation giving us x equals 0 and one equation giving us x equals plus or minus root 8. They can't both happen, and they would both have to happen either in this world where constraint's not possible, the constraint's not satisfied, or you're in this world where, how to put that? So the constraint's satisfied, obviously, but the gradients won't be parallel. Gradients not parallel. So it's conflicting information. It's not actually like, so the gradients not being parallel, right, would be kind of maybe like putting the cart before the horse. But we know the maximum is going to occur there. So if the max was going to occur, they would both have to be satisfied. We'd have to have the gradients be parallel, and we'd have to have the constraint satisfied. And we can't have both things. Like, yes, the constraint would be satisfied, but if the gradients aren't parallel, we know these are red herrings. These are misdirections. So that's why we're going to rule out y equals 0. You always should feel ready to make an argument about that, because you want to make sure you're not ruling anything out logically that you shouldn't be. But we can ignore this case of y equals 0. The same thing would happen if you did this problem and found that x couldn't equal 0. Found that x equals 0 as a possibility. X can't be 0. That's not allowed by this situation. So, continuing on this trend, you would have that 4 times this equals 1, or lambda minus 1 squared equals 1/4. Lambda minus 1 should equal 1/2, or lambda minus 1 equals negative 1/2, which would be lambda equals 1/2, or lambda equals 3/2. Now, these are still 2 cases to check. If lambda equals 1/2, going back to either of our starting equations, you'd have that y equals 2x times 1/2 minus 1, which is negative x. So if y equals negative x, then we'd have x squared plus negative x squared equals 8, or 2x squared equals 8. X equals 2, which would imply that y equals negative 2, or x would equal negative 2 from that equation, and y would equal positive 2. Either way, we're getting 2 critical points from this situation. 2 and negative 2, and negative 2 comma positive 2. And that was just from x equals, or lambda equals 1/2. What about lambda equals 3/2? Well, then y would be 2x times 3/2 minus 1, or the line y equals x. Y equals x would give us the equation x squared plus x squared equals 8. And we don't want to fool ourselves into thinking that this is redundant at all. 2x squared equals 8. Like, this work will look redundant, but okay, so x equals 2 now, but this is paired with y equals 2 because they have the same sign, they're not opposites. And x equals negative 2 would give us y equals negative 2. Just to go over, the y coordinate, the x work looks the same as the last time, but the y coordinates have ended up different because you're starting with different assumptions. Here y and x are opposites, here y and x are the same. So we have 4 critical points. 2 comma 2, 2 comma negative 2, negative 2 comma positive 2, and both negative. What does that give us for the f values? I'm just going to be lazy here, just stick f's in front of these all. F of 2 comma 2 is 12. 2 comma negative 2 is 4. Negative 2 comma positive 2 is also 4. And negative 2 comma negative 2 is also 12. So these are the maxes. And we have that max occurring twice. And we have a min occurring twice. So there you go. There's an example of how the algebra can get pretty tricky. My main advice to you, please do not divide. There's lots of ways to cash the algebra out correctly. It gets really messy if you start trying to divide everybody. That's the main advice I'd give to you. Thanks for watching. Try the homework out. Done chapter 14, on to integrals in the next chapter. See you in those videos. Bye for now.